Thank you very much for letting me speak. So, yeah, it's about the construction problem. X is a smooth projective, complex projective variety. Well, then Hodge theory yields a decomposition of its cohomology groups. Into the PQ pieces. If you think of this as the RAM cohomology, then HPQ is the subspace that is represented by PQ forms. Well, and HPQ is the conjugate of HQP, where conjugation acts on C here. So one defines the PQ's Hodge number as the dimension of HPQ, and that's a refinement of the case-Betti number. So the sum of these Hodge numbers would give the case-Betti number of X. That's the PQ's Hodge number. And then let me write LPQ of X for the primitive Hodge number. So that would be HPQ of X minus HP minus 1 Q minus 1 of X. And maybe here P plus Q is less or equal than N, which is the dimension of X. And that's the primitive. PQ Hodge number. Okay. So we know some relations between these numbers. So the Hodge symmetries would say that HPQ is HQP is Hn minus Pn minus Q, where this comes from their duality, and this is just that statement. And then the Hart-Lefschetz theorem implies that there are certain inequalities among these numbers, namely HPQ minus, let's say HPQ is bigger or equal HP minus 1 Q minus 1, where P plus Q is less or equal to the dimension. So these primitive numbers are always natural numbers. So I draw these numbers in such a table, which is called the Hodge diamond. And here H00 is down there, H10, H01, and so on. Each dot denotes one of these numbers, and N is the dimension. And these symmetries say that it's symmetric if we reflect at the middle or at this axis. And Hart-Lefschetz says that the numbers become larger if we go up here. Okay, so the question I want to address is pretty natural. It's the question which numbers can occur. So we know that we have some constraints, and the question is, are there more constraints, or which numbers could occur, or which Betti numbers could occur? That would be a weaker question, and one could also ask this question just for a single cohomology group. So maybe not for the whole diamond. That's a rather strong question, but maybe just ask which dimensions can appear here in such a decomposition. And the second question would be, are there more inequalities? So we know one of them, but maybe there are more. And in particular, so this question is pretty difficult, I think, but I will concentrate on a weaker question, namely inequalities of Lefschetz type. And thereby I mean similar inequalities of this shape. So inequalities among two Hodge numbers, that one is larger than the other. And so these questions can be found in Simpson's survey paper on the construction problem in algebraic geometry, and he is not very optimistic about those questions. So there is the speculation that maybe the outer numbers might be smaller than the middle ones. And in most examples, it's indeed the case that the outer ones are smaller than the middle ones, like hypersurfaces or products. Yeah. Also, there's a natural cup product map, and so one might expect that, like, two numbers here have a cup product to another number up there. So this might be bigger since there is a, yeah. Okay, so I have two theorems where I address these two questions. So the first theorem is the answer to the first question, where I don't look at the whole diamond, but a certain subcollection of numbers. So let us fix a dimension n, and then we look at a collection of numbers. Let h, p, q, p plus q less than n. So I don't look at the middle row, but only at the numbers that are below. Well, a symmetric collection. So symmetric means that the Hodge symmetries should be satisfied, and then we need that h00 is 1, and that hpq is larger or equal than at hp minus 1, q minus 1. So these are the constraints we know, and then I have additional assumptions. So assume further. First one is that LPP is bigger or equal Pn squared over 4. So the primitive PP's cohomology groups have to be larger than some constant, which doesn't depend on the collection, but only on the dimension on P. And the second one is that there's an integer k such that h p0 is 0 for all p not than 0 or k. So this condition means that most of the outer Hodge numbers have to vanish. Most means, well, h00 is 1 and hk0 can be arbitrary. So these are the assumptions, and then the conclusion is there is an n-dimensional smooth complex projective variety X with hpq. X is equal to hpq for all pq. So maybe I should draw a picture. Oh, okay. So I tried to draw the region which is constructible. And this is constructible as long as these HPP grow in a certain sense. So the difference has to be larger than this constant. And, well, we have zeros here on the. So, okay. So that's the result. So let me tell you three consequences of this result. So the first would be that if we look at the case cohomology group only, then more or less all Hodge numbers can appear, can have arbitrary Hodge numbers. Well, that's not quite true. If k is even, then h k half is to be bigger or equal than a constant. And maybe let me make a remark. So this constant comes from algebraic classes. And so it would disappear if we would look at sub-Hodge structures. Okay, so there's always the hyperplane class, so it's clear that this number has to be larger or equal than 1, but I don't know whether these constants are optimal. Probably they are not. And yeah.
But I mean, there is an important caveat to your result, so the dimension has to be larger than 8.
Okay, so then I need another remark. So, well, I maybe only say this. So that's right. This result we get only if the dimension is larger than k. Now one can try it and do a stupid thing, like if we want something in dimension n with interesting hn, then we could apply this theorem in dimension n minus 1 and multiply with p1. And this gives like all Hodge numbers, but they have to be even and the outers have to be 0. So we still get something. And yeah, in general, it would be false, so it's not true. But we will see this later. But that's true. OK, then the second corollary. So if we look at Betti numbers, say a formal vector of Betti numbers, meaning that the odd ones are even and they have to grow according to the Hart-Lefschetz theorem. Well, then again, b2k minus b2k minus 2 has to be larger or equal than a constant. Then there is x of dimension n with these Betti numbers. Well, for all k different from the dimension of n, so I can't say anything about this. But for instance, this, so why is this true? Well, it's true because we have zeros there, so we can just build, we can just apply this the theorem. And an amusing consequence is that if we are in even dimension, so if n is even, then there is no restriction on the odd dimensional cohomology, so everything can happen for the odd. And then a third immediate application is there are no inequalities among HPQ, well, where p plus q is less than n. This also follows immediately. So in general, I have no answer to the question which inequalities might appear. It's probably not so easy. So one can do it for Betti numbers, but for Hodge numbers it's difficult. So I will concentrate on a weaker question. Well, the most easiest form of inequalities that one might think of. So I'm looking for a universal inequality like this one, which holds for every smooth complex projective variety in dimension n. And number 3 says that if we have such an inequality, okay, sorry, no. Yeah, no unexpected. Something like this.
But I mean, even here, I mean, it's a bit misleading. I mean, so can't you have some sort your result is about the total Hodge numbers. But
So what's the question?
So I'm saying, I don't know your construction, but a priori your Hodge numbers that you get there, kind of to get anything, can be obtained by some sort of silly things like, I don't know, I mean, kind of, you have to decompose the Hodge structure in irreducible pieces, and maybe there are some.
No, I mean, if you, well, okay, no, I think I don't get the question. Sorry, I think I don't understand the question. So all I'm saying is that if there is a universal inequality, a linear inequality among those, so which might involve some differences, a linear inequality among Hodge numbers where p plus.
Okay, that I agree, but maybe if you look at some sort of primitive in certain sense, Hodge numbers, there might be inequalities.
Yeah, okay.
But sort of like simple Hodge structures, right? You could ask. I mean, it's totally a different question, but you could ask.
Sure, I don't claim this. Yeah. Well, I don't know. I don't know.
So can I just to make it clear? So you start with some vectors which have some constraints, right, because of the zeros on the side. But then your statement 3 is general. So
well, yeah. So if we have some inequality among the Hodge numbers below, then write it as a positive linear linear relation among some of the primitive ones is larger or equal than a positive sum over another couple of primitive ones. And then here we can make one very, very large and all the others are bounded. So if we have something like this, then we see that.
no, but my question was simpler. I mean, your result is general regardless of the hypothesis on the vectors having these zeros on the extremes.
Right, but it's kind of explaining the argument. I mean, you can make one of those things big, and you can make another one of those things big. Some little argument.
Yeah, but it is a general result. Number 3 holds in general, so that's all.
Yeah. Okay, so maybe then one can say more. I should say one more thing. So this in particular implies that if we have an inequality which holds in sufficiently large dimension, then it comes from hard Lefschetz. So that's maybe the last thing which I said to number 3. Now we look at a very simple kind of inequality, and I say that HRS dominates HPQ if such an inequality holds for all n-dimensional x. And C1 and C2 are some positive real numbers. So this is a sort of this type. Mm-hmm. Mm-hmm. Yeah, so that's important. If I look at all n, then something like this can only happen if it comes from the hard Lefschetz theorem because of number 3. Okay, so the second result has 2 parts. H11 is bigger than H20 if n is 2. And second, any domination in n bigger or equal to 3 comes from the hard Lefschetz theorem.
Number 1 under corollary, is that
Sorry, what was that?
Is K arbitrary in the first one, or is it the K that comes out of the theorem?
Right, so we fix some K, and then we fix some dimension which is larger than K, and then number 1 is okay.
Okay.
So there, I mean, here it's just
But K is fixed. In the sense of
K is fixed. Yeah. Okay, so let me outline how this goes. So number 1 is, well, we need that h11 is larger than h20 for all Kähler. So I claim that it's even true for all Kähler surfaces. And then, so it's not hard. Without loss of generality, S is minimal. Blowing up a point only changes this one, doesn't change that one. And then there's the classification of surfaces, and you check that if the quadratic dimension is less than 2, then it is okay. So without loss of generality, we are in the general type case. And then the Bogomolov-Miyaoka-Yau inequality holds, which says that C1 square is smaller or equal than 3 times C2. So these are the Chern numbers. And this translates into an inequality which implies this one. So in dimension 2, Chern numbers can be expressed in terms of Hodge numbers. And so we get, this is really an inequality in Hodge numbers. And you see that this is, in fact, a strong inequality that one, so it implies that one. So this proves 1. Well, and I can't prove 2, but I can give you the ingredients. So theorem 1 won't be enough because we don't say, I mean, here we can choose K, and so we can, yeah, we can make one of these numbers very large and the rest is bounded. But we have no control on the middle dimension, so we need new examples. Still, but theorem 1 is good for everything which is below the middle dimension. Then we need a new example. And that's the following proposition. So fix the dimension n and A bigger than B, natural numbers whose sum is n. Then there's an n-dimensional X with such that HAB of X is very large and HPQ of X is 0 for all P less than Q. So the picture would be something like this. I'm saying that most of the HPQ where P is not equal to Q is 0. So I don't claim anything about the HPP, so they might be pretty large. But then, apart from the middle axis, everything is concentrated in 1 degree in the AB degree. So this one is pretty large. I don't see a problem. PQ is not?
PQ is not AB.
Oh, yeah.
Well, but A is bigger than B and P is less than Q, so it can't be.
Yeah, for all other than those. Yeah. So that's the picture. So, yeah, so one has to use these examples and the others ones, and then maybe products with curves or something like this. And then one sees that in higher dimensions, no such dominations can exist. But it's maybe surprising that in dimension 2 there is such an inequality and there might be others in higher dimensions. So, yeah, I don't know.
So how do you construct these X?
So I construct a singular variety which has this shape and where actually the middle thing is small. And then one has to be very careful, and it's rather a mess to construct a resolution of singularities where only those change and the others don't. And I will show you at least the quotient that the singular one will appear. I tried to explain how the ingredients to theorem 1. But yeah. So that's the second part. So I tried to explain how one can build something where one can realize such a Hodge diamond. So step 1 is we look at the hyperelliptic curve, which on an affine piece is given by the equation y squared is x to the 2g plus 1 plus 1. So that's the normalization of the projective closure of this curve. This is a genus G curve, and it's a very nice one, and it has a lot of automorphisms. So if theta is a primitive 2g plus first, root of unity, so something like this, then we get an automorphism which maps x to theta x and y to y. And then we have the involution, the hyperelliptic involution, which maps xy to x minus y. Okay. So this automorphism is useful because the 1-0 classes of CG can be described as follows. So that's this direct sum from I equals 1 to G. And it's generated by these classes. So x I minus 1 times dx over y. And so psi acts on it on omega I with eigenvalue theta to the I. And on omega j bar, it acts like theta to the minus j. And since theta is a 2g plus first root of unity, those eigenvalues will be different for all ij between 1 and g. So this action on the first cohomology of CG splits up this cohomology group into eigenspaces with different eigenvalues, and each eigenspace has dimension 1. So that's useful in the next step. where we consider the product of this curve k times. And we choose integers a larger than b, maybe larger or equal than b, such that h plus b is k. And then in the second step, we find a group in the automorphism group of this product, such that the invariant cohomology so such that the invariant cohomology has Hodge numbers HAB, HBA should be G, HPP are bounded, so I don't want to write down the exact bound. And all other HPQ are 0. So it
HPP, so I think to me, does it bound it independently of G otherwise?
no, I mean, I think it's something like less. Okay, no, I think it's the minimum of P, let's see, plus 1 and B plus 1. So for instance, if B is 0, then HPP will be 1 for all reasonable P's, so it's as good as we can get, since there's always a hyperplane. And if B is not 0, but larger, then it will be the minimum of P plus 1 and B plus 1. So for instance, H11 will be 2 in this case. So the stuff in the middle is pretty small. Okay, so this would be an example. If we construct such a group G and we take the quotient, then this quotient has cohomology of this shape, where even those are very small. And then the question is what happens if we resolve the singularities. And in general, one will introduce a lot of new stuff and destroy everything. But in particular cases, one can be very careful and only introduce PP classes. So that's how proposition 1 goes. So maybe I give you one example how an element in this group might look like. So one typical example of an element in G would have the following shape: psi I1 times psi IA. Oh, no, so okay. So I act on each of the factors with a power of psi, and I want to have the condition that the sum of A1 up to AA minus the sum of the remaining indices should be divisible by 2G plus 1. And so this is precisely the condition one needs in order to fix the following class. This fixes So for all j, we have this 1, 0 class on the curve Cj, and we have a projection I to the ith factor, and we can pull back this class. And then this product will be invariant under this action. Because psi acts here by a multiple of theta, and then this condition means that theta to the sum is 0, is 1. Okay, and here j goes from 1 to g, and these are precisely the invariants, and one can check that this kills more or less everything else. And then one also we also have the symmetric group and this involution, and so yeah, the symmetric group can act on the first A factors and on the second B factors, and then one has to correct them by the involution so that this stays invariant, and in this way one can construct this group G. Okay, so I already mentioned the problem is that this is very singular. Okay, so instead of trying to resolve the singularities, we have to do something else. I mean, that's one way, but we will only get something like this, and it doesn't, yeah, it's messy. So the third step is known as the Godot-Serre construction. It's the following lemma. If Y is smooth, complex projective, and we have a finite group action, which is free in codimension n. So meaning that if you have an element which fixes something which has codimension bigger or equal n, then this element is the identity. And if we are in such a situation, then the quotient contains a smooth n-dimensional variety. Then there's an n-dimensional smooth variety x in this possibly singular quotient. And the cohomology is just given by the G invariance of Okay, so the proof is not difficult. One looks at the complete intersection in Y, which is G equivariant. And if this complete intersection has dimension n and it is chosen generically, then it won't meet the fixed locus of this action. So G acts freely on this complete intersection in Y, and so we can take the quotient, and X will be the quotient, and it will be smooth by Bertini's theorem, because the complete intersection here was smooth and G acts freely on this complete intersection. Maybe I continue here. Okay, so using this lemma, we are reduced. We don't care about the middle dimension, and the reason is because we want to apply Lefschetz, and we want to apply this lemma, which only tells us something about the cohomology below degree n. So in order to produce this x, we are more or less reduced to constructing a smooth projective variety y with a G action such that the invariant cohomology has this shape. And y can have arbitrary large dimension. So maybe the first example would be what we could do is the following. So we look at the group from step 2, which acts on this product, and then we extend it to the product of this product curve with a projective space, namely the projectivization of this guy, where G is just a symbol, and G acts here by permuting. Like G, an element H here maps this vector to H times G, this vector. And this is free in codimension n if L is large enough. Well, because it permutes here a lot of stuff. So this would be an example of such a variety y where we can apply this lemma, and the cohomology projective space has not a lot of cohomology. The invariants here are, well, they are concentrated in a single degree, so we get an example where one number is large and the others are small. And, well, yeah. So that's not enough. Yeah, so one could try to introduce more factors here, but this doesn't work because then one has this product of an invariant class here and an invariant class of another factor, and this gives more invariant classes a little, yeah, further up in the Hodge diamond, and this would not allow us to construct something like we want. So we need another construction, and this is example 2. So let I be a finite set, an index set. So in the application, this index set will run over the numbers that we want to manipulate, the Hodge numbers we want to manipulate. And then for each index, we have a group action gi, ai, bi, gi from step 1. And the genus as well as this dimension depends on I. And maybe we call this variety Ti. Okay, so we look at this, and then we need to do the following. So find an embedding of gi into the general linear group of some vector space, Vi. And I want to do it in such a way such that I can embed Ti into the projectivization of Vi in a gi equivariant way. So gi now acts on this projective space, and this embedding should be gi equivariant. And then the product of all these groups acts on a large projective space. So we sum up all these vector spaces Vi, and then we add a sum which is similar to the sum up there. Okay, and again, if we choose L sufficiently large, then this action will be free in codimension n. And now the idea is to, so Ti now, Ti lives in this projectivization, so it embeds into this large projective space, and they are all disjoint. And now we can blow up all of them simultaneously and get interesting cohomology, and this will be what we need. So yeah, so to the blow up of Pn, where Pn is this large projective space. It lifts, and if L is large enough, then it is free in codimension n when you have to check this. So what I'm doing here is I try to construct an example where I can manipulate all the Hodge numbers that are neither on the boundary nor on the middle axis.
So you're doing, the first example works for just like A, B, just two.
Yeah, the first example only works for one number.
But then if you want to get all the different numbers, all at the same, like, all at the same time, yeah, I get it.
Yeah, right. If one wants to get all of them at the same time, one has to do something such that the cap product is always 0 between the different contributions. So a blow up of disjoint submanifolds might be a good idea, because then the cap product of cohomology here, cap with the stuff over there is 0 all the time. And that's somehow one condition one needs if one wants to manipulate all of them independently.
Okay,
so products don't work, but this blow up of disjoint submanifolds is a way. So the first example has the advantage that, well, it manipulates something. It only manipulates one number, but the number can be on the boundary, so it manipulates HK0.
And then kind of makes all the other guys small.
Right. The others are small, and then we can combine example 1 and 2 and get the theorem. So in order to see what this blow up does, let me recall. I think I don't need this. So if that in Y the smooth of codimension R, then the blow up has Hodge diamond. We have to start with Y and then add tail twists of the base. So where I runs from 1 to R. And okay, so I guess the picture would look something like this. This is the Hodge diamond of Z. And that's Y. Then the blow up has has the Hodge diamond where we start with y and then we add Tate-Twist of z. So we shift z by 1, 1, 1 up and add it, and then we shift it again and add it, and shift it again and add it. Now in this example, we blow up Ti, and the action of G on Ti, the invariants are concentrated at 1 degree. So if we only look at the G invariants of this blow-up, then each Tate-Twist adds more or less only to one Hodge number. Well, and so we get a contribution here and there, and here and there, and so on. But that's precisely what is forced by the Lefschetz condition. And we don't destroy anything else. So this is a way to manipulate one of these interior Hodge numbers. And combining example 1 and 2, one gets the example of the theorem. So I think I stop here.